Good morning, sir. My name is Shivangoda Patil. My topic is role of hydrated ions in aqueous battery stability and performance. Introduction to this topic is in aqueous batteries, metal ions like zinc, magnesium, aluminum exist in electrolyte as hydrated species, each surrounded by a shell of water molecules. This hydration shell profoundly influences ion mobility, charge transport, and interfacial reactions at electrodes. For instance, tightly bound water shells around multivalent ions create larger effective ready and stronger uh, solvation energetics, which slow ion diffusion and hinder solid state diffusion into electrode materials, adversely affecting rate capability and cycling stability. Strategic control of hydrated ion behavior through electrolyte engineering can boost aqueous battery performance in systems like hydrated intercalation for zinc-ion batteries. Water co-insertion with ions into cathode frameworks provide electrostatic shielding and structural stabilization, enhancing diffusion capacity and cycle life. Similarly, exploiting hydrated etiquette of water in salt electrolytes reduces free water activity, optimizes ions solvation, and enables formation of protective interfaces, extending the electrochemically stability window and suppressing corrosion and gas evolution, thus improving voltage range, Coulombic efficiency, and long-term durability. So here are the various synthesis methods. A role of hydrated ions in performance and stability. So solution structure determines key behaviors. Cations like zinc, calcium, and magnesium bind strongly with H2O molecules, increasing their hydrated radius and hydration enthalpy. This impacts dissolution interference, transport, and co-intercalation into electrodes. Co-intercalations versus naked ions. Strongly hydrated multivalent ions may enter electrodes with part of their water shell, affecting voltage kinetics and structural stability. Water in salt electrolytes. Superconcentrated electrolytes bind nearly all water into ion solution shells, suppressing free water. This lowers H2 evolution, broadens voltage windows, and improves interfacial stability. Hydration of ions. Structure and energy. Inner versus outer hydration spheres. A cation in water is surrounded by an inner shell of water molecules tightly coordinated to it and a looser outer shell held by hydrogen bonds. Hydrated radius and enthalpy matter. These values vary with ionic charge and size. Smaller or more highly charged ions bind more water, forming larger hydration shells with coordination energy that influences whether ion shed water dissolvent before entering electrode hosts. Now we will discuss influence on aqueous battery behavior. First one is dissolution at interface. Second one is water in salt electrolytes. Hybridization strategies. Hybrid solvating electrolytes common in sodium or zinc based aqueous batteries. Strong solvents, weak or anti-solvents. Now we'll discuss about solid liquid hybrid electrolytes. In these, for a solid state batteries, liquid electrolytes are infused into ceramic or polymer matrices to ensure ionic pathways, reduce interfacial contact losses by filling voids, still face interface formation challenges between solid and liquid phases. Now we'll discuss some hybridization strategies which will go through detailing. Ionic liquid or aqueous water in IL hybrids. Mixing ionic liquids with tiny water amounts and high salt loading creates water in ionic liquid systems. These extend electrochemical windows, improve thermal stability, and suppress vaporization, suitable for aqueous hybridized designs. Co-solvent and additive hybridization. Adding organic co-solvents into aqueous electrolytes lowers freezing points and modifies hybridization networks, enabling stable operation under extreme temperatures. In, in zinc systems, mixing anions in optimized ratios yields synergistic effects, boosting capacity, suppressing zinc hydroxide precipitation, and improving cycle life. Environmentally friendly hybridization. In this emerging push for fluorine-free or greener diluents in non-aqueous electrolytes, replacing persistent fluorinated molecules to maintain solution benefits while reducing environmental footprint. So now here we come to the conclusion of this topic. So aqueous battery performance is fundamentally governed by behavior of hydrated ions. Their solution structure, hydrated radius, and dissolution dynamics at electrode interfaces dictate kinetics, stability, and voltage limits. Tightly bound hydration shells around multivalent ions like zinc, magnesium, aluminum increase energy barriers for intercalation and can induce co-intercalation of water, stressing electrode materials if not properly managed. To counter these challenges, hybrid electrolyte designs, including water in salt systems, solvent blends, ionic liquid, aqueous hybrids, and hydrogen gel based media, intentionally restructure solvent environments. These approaches reduce free water, promote anion-rich solution sheets, suppress hydrogen evolution, and extend electrochemical stability windows up to 3V by pairing such tailored electrolytes with engineered electrodes. Hybrid aqueous, non-aqueous electrolytes even enable high voltage Li-ion cells with energy densities near 160 Wh per kg over 1000 cycles. Overall, this integrated strategy, controlling hydrated ion behavior via hybrid solution and co-designing compatible electrodes, is unlocking aqueous battery systems and approach the safety, cost effectiveness, and performance of the non-aqueous counterparts, paving the way for next generation and energy storage solutions. Thank you very much.